Let's take a brief look at the spectrum of electromagnetic waves, or the electromagnetic spectrum. You can see that starting from the low wavelength high frequency range, we have first gamma rays and then X-rays, ultraviolet, the visible spectrum, the visible light in the infrared region, and then microwaves and radio waves. So radio waves are the ones that have the longest wavelength, up to basically kilometers range, and the gamma rays with the highest frequency have wavelengths in the picometer range or less. As for the visible portion of the spectrum, here we have the wavelength varying between 400 nanometers and 700 nanometers, going from the low wavelength high frequency region violet all the way up to red, which is the high wavelength low frequency portion of the visible spectrum. Okay. So we have some overlaps in frequencies for some of these waves, so it depends on what you want to name it. So taking a look at the properties of these rays, for gamma rays, the wavelength region 1 angstrom to 10 femtometer, frequencies 10 to 18 to 10 to 22 hertz. They're emitted by radioactive nuclei. They're highly penetrating, very harmful for the living tissue. The best shield to protect from these rays is to use thick lead wools. X-rays, next in line, are in wavelengths 10 nanometer to 1 picometer. So in this range, you can see here, frequencies 10 to 16 to 10 to 20 hertz. They're produced by stopping high energy electrons upon bombarding metal. As you know, X-rays are perfect diagnostic tools, and they can be used to study the crystal structure because we can have wavelengths in the angstrom range with X-rays, which is comparable to the atomic spacing in crystals. Ultraviolet waves, the wavelength 0.4 micrometer to 60 nanometer range typically. Frequencies 10 to 15 to 10 to 18 hertz. The sun is an important source of ultraviolet waves. These waves are absorbed by the ozone in the stratosphere, which protects the Earth. Then we have the visible spectrum, visible light. 400 to 430 nanometers wavelength is violet. The frequencies are in 10 to 15 hertz range here. 430 to 485 nanometers blue, 485 to 560 nanometers green, which is where the human eye has the maximum sensitivity at 550 nanometer, that corresponds to green. 560 to 590 nanometer yellow, 590 to 625 nanometer orange, and 625 to 700 nanometer is the red region in the visible spectrum. Then we go to the infrared region. Infrared waves have wavelengths 1 nanometer to 70 micrometer, frequencies 100 gigahertz to 10 to 14 hertz. So in this range, they are produced by atomic vibrations. So when absorbed, because these waves will match the natural frequency of oscillations of the atoms, they will cause heating. They're used in physical therapy, infrared photography, in order to detect materials, for example, and vibrational spectroscopy to characterize the vibrational modes in crystals. Then we have higher wavelengths, microwaves region, 0.3 meters to 1 millimeter wavelength, 1 gigahertz to 1 terahertz. So that's in this range, 1 gigahertz to 1 terahertz microwaves. They're generated by electronic devices. They find use in radars and microwave oven. And finally, we have the largest wavelengths for radio waves. Radio waves can be from 0.1 meter lambda to 10 to 4 meter, 10 kilometers. Frequencies kilohertz to 10 gigahertz. They're created by charges accelerating in conducting wires. as we have seen in the half-wave dipole antenna, radio and television communication can be achieved. So as you can see, I always have a lambda and f corresponding to it. What is the relationship between lambda and f? If you remember, these are electromagnetic waves traveling with the speed of light. So c is equal to lambda divided by the period, or lambda multiplied by the frequency. So if the wavelength is high, that means the frequency is low. If the frequency is high, that means the wavelength is low.